Hi everyone, and thanks for attending this community meeting. Today we're gonna talk a little bit about Restate 1.3, what we did there, what are the new features, and also a little bit about the new internals, how the journal works, something you've probably heard already. There's a project called ShareCore, part of the SDKs, and and then we take it from there. So let me share my screen. All right, for who doesn't know me, I'm Francesco Guardiani. I work in Restate and I'm working pretty much on the SDKs, developer experience, and API reviews when you interact with Restate. And again, today we're going to talk about with the new features, and then we're going to go under the hood and see how things work. So, for who of you that has not seen the blog post, Restate 1.3 has features in three major categories. One is that now support what we call the deterministic resilient concurrency, which is this ability of executing concurrent operations and then await the events in a way that you can deterministically await them always in the same way. Then we have support for fine-grained control over service-to-service communication, which is a set of features that help you build things like task orchestrators. And then we also have improved our service catalog quite considerably, and now we have a good support for JSON schemas and the ways to generate an open API out of your service definition, and so on and so forth. So I would like to start just jumping straight to code. And as usual, this is a community meeting, so feel free to interrupt me and ask me questions. You don't have to wait the end for this. So we're going to start first by looking a little bit about at the features surrounding deterministic concurrency. Here we have an example where we have to do animal verification. And to do animal verification, you need to send an email with a link. And in the Restate world, we can create await pens using Awakeabots. So we send an email with an Awakeable ID. And then you want to start a verification timer such that either the user clicks on the link first, or you want to wait for the verification timer to expire. And then we also want to add another timer, which is a reminder that we say every 5 seconds, for example, we send it to the user a reminder asking to click on the link. And the way we do this with the new deterministic concurrency features is that we have, for example, here I'm showing Kotlin, but you got the same features in all the other SDKs. We use this feature called select that lets you essentially await either on the Awakeable to complete, which means the user clicked on the link, or the reminder timer was fired, meaning that you need to send a reminder email, or the verification timer fired, meaning that the verification expired. Here we are essentially reading on 3 events that are intrinsically concurrent. And first one that fires completes this select, and then if we have verified, we don't loop anymore. If we still need to verify, we loop again. So, and I'm going to show you actually this running and show you how this completes with Restate, and in fact, Restate is resilient and is able to replay it deterministically. So let me go over here. We have our Restate UI, and here I will register the services just for simplicity. And I go here in verify email, where you see also I get auto completed with an example body shape, but that's because now we propagate JSON schemas to the Restate server, meaning that the Restate server knows whether it's the JSON object that our services is expecting. And let's say I want to send an email to me. So I want to verify my email, and I was Linky developer. And here I'll send a request. And we can see here in the console that we got invoked. We sent the email the first time. And then we have here the sending reminder email that is happening every now and then. That's because we are in this loop, and every time we will select the branch where we have the reminder time. If now I kill this, what do you expect from restate? You expect that restate will be able to restart the invocation from the point where I left. And you can also see here in the journal that we sent the different, we started executing the invocation, then we sent the verification email, then we created a first timer that is the verification timer that is 24 hours long, and then we created these reminder timers. And here we see that the invocation is stuck because cannot reach the SDK. So now we go back and we restart. We see that we very much restart from the point where we left. So we start from the reminder. In this case, was probably reminder. There you go. We start again, and this was probably the fifth or the sixth reminder here. And just to complete it, let's try to compute this signal here. So we take the unbreakable ID, which is this string that starts with the signal underscore. And we go here, and we complete the awakeable. And this completes the verification process. For sure, I closed the other window, but this completes the verification process. So that's just a simple example of how you can await concurrent events. And then
maybe a question in the meantime. We had someone in the chat asking, how do you recover in cases where the journal is corrupted, missing, or lost?
Well, I mean, first of all, the restate cluster stores the journal, persists it, and replicates it across nodes. So if you have a cluster of 3 restate nodes, depending on your replication factor, of course, you will have more nodes in the same journal. So that's first like something important to say for people that don't know it. And generally, the idea is that when restate tries to replay, when it loads the journal, it of course does some sanity check to make sure that actually the journal is sane. If the journal is not sane, it won't try to reply or to re-execute it. But we also right now don't imply anything like checksums or anything like this in place to make sure that the journal is actually correct. When we reload it. Does that answer the question?
I think for now it does. I think you can continue in this app. What consensus algorithms do you use to maintain consistency across different journals, across nodes? Can you manage multiple failures?
Yes, we can manage multiple failures. There's actually, there was a community meeting, I think it was the previous one, right? Or the 2 community meetings ago. We actually went pretty deep on this.
I can post the link to that community meeting here in the chat as well, together with a blog post which explains a bit more about how this works.
Yeah, I think it's better because it's a reasonably long topic.
All right.
But yeah, so this one is one of the examples about deterministic concurrency. We got another example that is where I want to show you a classic example of fan out, fan in. So you got a service that just needs to execute some tasks in concurrently. So it gets the task definition, it splits it in subtasks, and then after that, it runs the tasks asynchronously, and then it just wants to wait, and then at the end it needs to wait for the results. So then it just a little note for people that don't use the Kotlin API. The Kotlin API is just a little bit of a difference from the other APIs. The run block is just context run, and run async is run block, but it returns your future that you can await later on. So again, what we do, we split the tasks. We then schedule the tasks to execute doing this run async, and then we wait for all the tasks to complete. And I want to show you a little bit how this behaves. So let's go here in fan of worker. No, sorry, is this fan? Yes, this fan of worker. Okay, let me just give a list of comma separated task list, A, B, C, D, E, and G. All right. And now you can see here, all right, all the tasks that completed. And this is already retrying because some of the tasks, they have a Boolean, random Boolean fail or not fail. And we can see here that we have a journal where some tasks completed and other tasks did not complete. And now we just read a little bit, and actually this is going to work fine. But another thing that I want to do here actually is that I want to cancel. So, I canceled too late probably. I probably canceled too late. Let me try again. Okay, let me send the record. Yeah, I canceled too late because everything was done afterward. Let me try this again, and then, all right, it got this, one of them is failing, and then let me try to cancel it now. Okay, and the reason I'm showing you this is that one of the updates of Restate 1.3 is that now canceling context run actually works completely fine. And another update of Restate 1.3 is that now you will see the cancellation in the journal. So here we see that we are, again, we have this journal where we started by splitting the tasks, then we have these tasks, and then we try to run all of them concurrently. But then when awaiting all of them, we got a cancellation. And what we did after the cancellation is that we just ran a sleep to make sure that we can read the journal. So nothing special. But the point is that now you can run multiple side effects in parallel, await all of them in parallel, and then at the same time you can await for a cancellation to come, and eventually run the compensations in case you are building a saga or something like this. This is extremely helpful. So we have a use case that previously, unfortunately, I don't have the code here, but we have a use case here in the sagas. I think it's somewhere examples. Yeah.
There's also a guide on this topic in the documentation guides.
True. There is a guide on this topic. But the cool thing about Restate 1.3 is that now you can go here. Let's see, show the code, right? And now the saga here can essentially await in parallel all the different operations. And also here, it can fire all the operations and then await all of them in parallel. And then eventually execute the compensations. And all of this will just work fine, essentially. So, and the reason why this is so important, like the deterministic part of the deterministic concurrency is so important is that because Restate requires your code to be deterministic, it requires that you can replay in the same order that you executed the code the first time. Then with this deterministic concurrency, you are actually able to essentially await any events to happen at a given point in time and take on each replay the same decision of which event you take. I'm going to go a little bit into the details of this in a few minutes. And okay, so this is for the deterministic resilient concurrency. I want to just touch a little bit on the new features about service-to-service communication, because those are actually were very highly requested from people. So let me go over this. Okay, so we got another use case. This one is a very much task orchestrator use case, where we got a task runner that just orchestrates the different tasks to run, and then a task service. And the task service is just a lock that sleeps for a random amount of time, easy. And then we got the task orchestrator. Now the task orchestrator receives a request to start a task, starts a task, and then it remembers about it. And then it has a get task result to retrieve the task over the result at a later point in time. And then it also has cancel them all, which just takes all the tasks and cancels them. Now, to start a task, we do business as usual. We just send a request. You use a send to start a task. But then what we now can do is that we can add a potency key. And on top of this, we also now propagate back to the caller service. We now propagate back the invocation ID. So when I do a request, I can also get the invocation ID of the request that I just made. So now when I start a task in this task runner, what I do is that I send the request to start the task. I provide an input in CK, I get back the invocation ID. And then I just store it. This is a virtual object. So business as usual, I just I store in the map of the tasks that I started. And then in the get task result, what I can do now is that I get the task invocation ID by reading my state. And then after that, I can use the functionality called attach. Now, this functionality just lets me connect to an invocation that either just started, that either is still running, or it was already completed, and get back the result when it will be available. So in case the invocation is still running, I will connect to it and listen for its result. Or if the invocation completed already, I'll just get back the result immediately. And this attach is like all the other asynchronous methods of the context, meaning that it will transfer back a doable feature that then I can put inside, for example, a select or an await all, use deterministic concurrency essentially. And the third method, cancel them all, what it does is something similar to the previous method. So it takes all the running tasks that I started, and then after that, it will use again the same API invocation handle, then to cancel the task. And this cancel behaves like the cancellation that you trigger from the UI. So it sends the signal to execute the cancellation, which gets written to the journal, and then this signal it gets processed by the call list service. So in 50 lines of code, we wrote a very simple task orchestrator that is able to start invocations, making sure you start them once, keep track of the invocations you started, get back the results of these invocations, and then be able to essentially do the cleanup and cancel them all when you don't need them anymore. So I think this is it for what it belongs to the new features. The improved service catalog is, well, you saw it. So like now you see that this playground is something we already shipped in 1.2, but in 1.3 we expanded it, and now it's just much more filled with details. And the schemas are just much more rich. And also all the SDKs now will propagate out of the box more or less the schemas. So I mean, it doesn't matter which language you choose, you will get these schemas. And depending on the SDK, you can tune how the schema gets generated. All right. Do you have any questions about this part? All right. I just want to conclude this section saying thanks for your feedback, really. The features that you see here that we worked on in 1.3 were features that people very much requested for. And as usual, as we like to say in Restate, we also like to drive our roadmap based on the community feedback. So thank you so much for this. It's very, very helpful. All right. So I want to go a little bit now in the section where I talk about how everything here works under the hood. So for all of you that knows Restate already, you know that at the very high level, when you send a request to Restate, you send a request to the Restate cluster. The Restate cluster will then persist invocations, replicate them, and then start sending the request to your service code that ultimately hits your business logic. When the Restate cluster does request to the service code, it does it by doing HTTP request, and it transports back and forth what we call the journal. The journal is where we store the invocation progress. Now, in Restate 1.3, we did a huge update to this journal. And we modified the data model to make sure we could represent new things inside it. I'm going to get back to this in a second. And the important thing, and what I would like to stress out, is that this journal data model is actually really the representation of the APIs of Restate. So when you do something inside a context, you write an entry to the journal. And this means that effectively how this journal works is fundamental to the semantics of the Restate as a system. Now, this new journal is what we call the append-only journal. And I want to show you here a little bit of an animation of how this works. So you see on the right, you have code. You can imagine this being TypeScript, but it works the same with all the other languages. We do a context sleep, which returns me a future. Then I do context run, which returns me a future. Then I await the context run, and then I wait the context sleep. And then you see on the left what Restate writes for any of these operations. So when you do context of sleep, it will write what we call a command for sleep. Then when we do context of run, we write in the journal a command for run. Then eventually the run completes, and we write a completion for run. And then eventually the sleep completes, and we write a completion for sleep. What we did with this new data model is that we now write separately commands and completions. And we establish a total order between the command and completions. Now, the commands are driven by your code, of course. This means that it literally depends on whether you write in your code first context sleep or context run. If you swap line 1 and 2, you will have in the journal in the reverse order the commands. While completion order really is not something that depends strictly on your code. It's actually intrinsically non-deterministic. And you can have first the completion for run and then the completion for sleep. But you can also have the vice versa. So you can have the completion for sleep first and then the completion for run first. And the reason why this append-only journal really is helpful is that now we record which of the two completed first. So you can see how we essentially profit from knowing which of the two completed first to implement the deterministic concurrency. If you imagine line 3 and 4 rather being promise.any, I can deterministically always choose either one or the other because I have this order recorded in my journal. So yeah, what are the benefits here? Obviously, we can now do deterministic concurrency thanks to this total order. But also we have a good paper trail that is very useful for an inspection, in particular if you are in environments where you have constraints that are about compliance, restrictions, and things like this, then this is really helpful in that context. And then generally it also helps debugging. I don't want to spoil new features too much, but we are working on something in UI that will actually profit from this fact that now we store completions, the completion order, and will help you much more understand, essentially, visualize exactly how things went inside your invocation. And then they will help you a lot more to actually debug effectively what happened in your invocation. And one of the things that we did with this new append-only journal is that before we had let's say a specialized design for context run. We had in the previous data model, we had entries, completions, and then we had context run, which was very much a special thing on its own. And now we changed this a bit with the append-only journal, and this new design actually allowed us to put context run inside the rest of the design. This is very important because thanks to this, context run now works fine when it interplays with all the other Restate features. Before, we had this issue where context run did not really work when you use cancellation, while now it works completely fine, and we can expect it to work as any other functionality inside the context. And then the last thing that I showed you already in one of the demos is that now actually the cancellation is a message that you see explicit in the journal. So you can, when you open the journal view, you see cancellation happening here. And that's very helpful. Now, the journal is, of course, a data model. It's a data model that the Restate Server implements. But of course, we will wait to transport this to the SDKs, because then the SDKs are ultimately the library that you need to bring in your code to develop Restate services. Now, in order to do this, we have this protocol that we call the Invocation Service Protocol, shortened as the Service Protocol. And this protocol is essentially just sending protobuf messages on top of an HTTP to invocation string. And if you are curious and you want to know a little bit more about this, you can look at this link where you can see that there is a pretty much a one-to-one mapping between everything you have in the context API and a message that it goes on the wire. To give you an example of how it works, a normal restate invocation is that when the restate starts, it sends a start message to the SDK, and then every time you call a context method, let's say a sleep, it creates a sleep command message which gets sent to the server. The server writes this sleep command in the journal. Then the server, of course, registers the timer for the sleep. The sleep at some point completes, the timer fires, and it writes a completion sleep in the journal. And then after that happens, we send back a sleep completion back to the SDK. And the peculiarity of this protocol is that it is also able to manage replays, of course. So what it's able to do is that if you start this like the first time, it just sends a start and the input. And then the subsequent times, it will resend again, start the input and then the sleep and the completion to replay that part of that you have already executed. Now, as you can imagine, this requires a little bit of business logic in the SDK to implement this. And when we started Restate, at the very beginning, we had just two SDKs. We had just Java and the TypeScript. And back then, things were manageable. But then when we introduced new SDKs, we introduced in something like 3 months Python, Golang, and Rust. So to become a little bit more complicated, to make sure that all the SDKs were in sync, would support all the features. So we had to find a solution to this. And we came up with this project that we call the SDK shared core. So on the right, you see how more or less every SDK works. At a glance, it's composed by 3 layers. You've got the APIs, the context you interact with. Then you got the state machine, which is the implementation of the service protocol. And then at the bottom, you have the network, which is an HTTP server, essentially. And all SDKs worked like this even before we actually worked on the shared core. And what we thought to do is actually to create a unique code base, which is what we call the SDK shared core, for the state machine. And such that every SDK now works as follows. It has an API, that is the one that you use, which then interacts with the state machine, that is this SDK shared core. And then at the bottom, there is a network layer that is essentially just an HTTP server. This one is still separate and individual for each SDK because, for example, in TypeScript, we want to support Node.js, but we also want to support Dino, we want to support Cloudflare Workers, Done, and I don't know if there is anything else. I think it's this 4. In Python, we want to support ASCII, which has Ubicorn, Hypercorn, and a few other HTTP servers. So this network layer is just a little thin layer that really depends on the platform where you end up deploying your service. Well, the API layer is essentially like the experience that you get when you use the SDK. And the state machine is literally this implementation of this service protocol. And those of you that already looked at this, it's built in Rust. And we use it in the Python SDK using Py3. That is a binding generator between Rust and CPython. In the Golang and TypeScript, we're using WebAssembly. So we compile the shared core, WebAssembly, and then we ship it with the SDK. And then in Rust SDK, we of course use it natively. And why we did this? Well, I hope it's very clear tool, like just update one code base and then the SDKs profit from it. Just to give you a very simple example, yesterday a colleague of mine that there is a bug actually now we notify an error in the SDK, and I update the shared core, and then I just do a patch release of all the SDKs, and they will just get essentially the bug fixed. So that's pretty useful. And just to give you a little bit of an idea again about how this actually works, like the shared core as an API that is that it's not too far from the context API again. For each corresponding method in the context, let's say context.sleep, you got a corresponding sys_ method that is inside the shared core. And then when you await a feature, you have something that we call take notification that essentially lets you pull a notification from the shared core and just essentially surface it back to the user code. There's a who here that is I looked at this with attention. You've probably noticed that the sleep does not take the sleep duration as input, but it takes this wake up time since Unix epoch. That's because the shared core is designed to be a pure code base that does not execute any syscall, and this is what makes it easy then to compile it to WebAssembly and all of these platforms where you cannot access essentially the work clock.